Alright, the second transform that we are going to see is the impulse function, which is Dirac T. And the Dirac T has a unique characteristic. It has, for example, in this case, because T is termed as a time shift at 0, or in the more general sense, let's take Dirac of T minus T0. So this function, Dirac of T minus T0, always has got a certain property. It is 0 for T not equal to T naught. That means this function is always defined at T naught. So that's the first characteristic. The second characteristic is a Dirac function has an area of 1, which is very important. So if we integrate that from T naught plus a certain very small number, or minus certain very small number, to T naught plus a certain very small number. This in the time domain is, if this is T naught, we are trying to integrate it between a very small on the left and a very small on the right. And if we integrate this Dirac function T minus T naught with respect to time, it should give us 1. The sense is, the width of a Dirac function is very, very small, and the height can be as long as it goes, but the main important thing is the area covered by this Dirac function, which is the integration, should always give you 1. Which means if the limit of epsilon approaches 0, then this height should go to 1. Which means the total area has got to be equal to 1. These two are very important properties of a Dirac function. So once we define a Dirac function as this, and the first one is a Dirac function is always 0 for anything on either side of T naught, which gives us, so if we have got Dirac at T, that is essentially Dirac at T minus, I think I have to delete my, I have to remove here my auto shape. Yeah. Alright. So if I have Dirac T, which is essentially T minus 0, so we have T0 is equal to 0 here, then this function has got a value of Dirac T at 0, and on either side of it the value is going to be 0 according to the first definition. The second definition tells us that this Dirac function, the integration of this Dirac function is going to be equal to 1, which brings us to the Laplace transform of the Dirac function. So if I take the Laplace transform of a Dirac function, that's going to be, according to our definition, it will be from 0 to infinity of Dirac at t e raised to minus st dt. According to our definition for Dirac function, we have said that a Dirac function is defined only at that minus t naught value. So in this case, t naught is equal to 0, right? Therefore, this Dirac function has a function that only at t naught equal to 0. So if we, for example, split this function into 0 minus to 0 plus of Dirac at t e raised to minus st dt plus anything for the 0 plus to infinity Dirac at t e raised to minus st, then all that value is going to 0, right? Because Dirac function is not defined outside that limit. But for that limit, we know that the integration of Dirac at t dt has been 1 here, which would give us that the Laplace, that whole value is going to have that Laplace value information, because that's 1. If we substitute 0 there for e raised to minus st, it should give us 1, which gives us that the Laplace transform of Dirac at t is always going to be 1. That is another very important definition. So we have already seen the Laplace transform of the step function is 1 over s, and we just saw the Laplace transform of the Dirac function is 1. Alright, so we saw that and we saw that. Okay, now we have the shifting property for a Dirac function. The shifting property for a Dirac function tells us that any function, if we have any function f of t, if it is going to be multiplied by Dirac t minus 0, what does that tell us? And if we are going to take the integration from minus infinity to infinity, then this thing is essentially that function can be any function. Okay, that function can be any function, but the Dirac function is defined only at t0. At t0 value, that integration has a value of 1. We have already seen that. That function, when integrated with infinity, has a value of 1 only at 0. The rest is going to be multiplied by t0. So that function is going to have a 0 value for everything apart from t0. But at t0, it's going to have 1, and this f of t is going to have a value of f of t0 at that function. So except at this point, everything on the left and everything on the right is going to be 0. Therefore, this integration should give us a value of f of t0. So this is called the shifting property. This is a very important property in communication. So when you have a function f at t, if you are going to integrate that with a Dirac function t minus t0, then the only place that you are going to have a defined integration is at t0, because at t0 Dirac is going to have a value of 1. Apart from t0 or at any other point outside t0, it's going to have 0. So this result is going to give you f at t0. That's called the shifting property. This is a very important property with Dirac function. Alright, I wish we were in class where I could have asked if you have any questions, but if you have any questions while watching this video, please try to email me. I'll try to answer as fast as I can. Alright, next we are going to see the Laplace transform of some important functions, and as I have said earlier, first or the third, I should say, is a constant. Sorry, what have I touched? Okay. So the Laplace transform of a constant, as we have said earlier, can be rewritten as a constant times u at t, because u at t has a value of 1 as long as the function starts from 1, and that is going to have 1 over s. We have already derived, or we have already arrived at that function.